And so the first exercise here is to break the data into subsets. So what we're going to do is build a script that performs a correlation check between each gene and the blood sugar levels. So looking at all the individuals for that gene and checking their blood sugar levels and computing a correlation value. And what we want to do is sort the genes into two categories: those that have an absolute value of the correlation, so positive or negative, greater than 0.1, and we would call those correlated genes, and those that are less than 0.1, closer to 0, we would call low correlation genes. And what we want to see is how does our linear regression model perform when trained on these two subsets. So we have a high correlation subset and a low correlation subset. And what does our linear regression predict relative to the ground truth in those cases using those training data sets? And so this in the code here, the task is to complete this function for computing the Pearson correlation coefficient and returning it at the end here. So the inputs are simply the two variable vectors here. Okay, and then the second part of this exercise was to look at the logistic regression. And what we're interested in is doing a epoch step. So we have an epoch loop, and we have a function for computing the gradient of the negative log likelihood for the sigmoid function. So this has already been completed, and our task is simply to perform the update. So we have a set of parameters, and we want to get a new set of parameters by feeding in the gradient for the negative log likelihood and multiplying this with a step or a learning rate, which is supplied as a user supplied parameter or argument to this function. But in addition to that, we want to set up this learning rate scheduling or learning rate annealing concept. So not just a fixed learning rate here, not just a fixed step size here, but one that is adaptive according to which epoch or which iteration we're on. So it's going to start with a high value or a maximum value of the learning rate, and then get progressively smaller and smaller as the epochs advance. Then the result should be this logit function plotted with the probability on the y-axis here and the data points plotted along this curve, colored blue or red according to their ground truth. So whether they were a 1 or a 0. And the idea here is this should be separating these 1s and 0s as best as possible. And again, this x-axis corresponds to the logit, right? So that's the result of our training, or the linear combination of features here that we're plotting. And we'll also get an ROC curve here that we can use to evaluate the model's performance. So in this part, if we have a look at the exercise, so here you can see the gradient is set up here. So we have a function that is computing the gradient according to this equation that I showed you. So we have an analytical expression in the case of the negative log likelihood for a sigmoid function and the gradient of that. So we don't need to do that part. Actually, the only task here is to fill in the rest of the code here in this epoch loop. So we're going for each epoch, we're performing an update. And the key task here is to use this gradient function to perform this update step. And then the second problem here is to complete this prediction function. So this is for the fitting or the training. That gives you the theta, that gives you the set of parameters. And then to actually test it, we want to simply run our logistic function with our parameters on a particular set of data. So this would be the test data set if we do the test training split of our data for cross-validation purposes. So here's the solution to the first part. If we look at this Pearson correlation coefficient function, what I've done here is broken it down into components. So we have a line here for the mean of x for the first variable and the mean of the second variable y. And we can use that to compute the numerator, which is going to be the sum of the differences between the data and the mean for both X and the Y cases. And another way you could compute this is with a dot product, since this here is a sum of vector product here. And that's the numerator, and then we can compute the denominator of the function as well. So that's going to be, we can break this again into the standard deviation for the first variable and the standard deviation for the second variable. And then we put it all together, numerator divided by the two denominator terms, and then spit out a correlation here. And so what we see at the end when this runs is we get the data, the linear regression trained on all the genes, the linear regression trained on just the genes with high correlation, which looks very similar to the all genes version. And then if we try to perform the training on the low correlation genes, we see that we've basically broken our model. There's now no predictive capacity here. So the predicted values are not correlated with the true values when we run this test. And now for the logistic regression part. So to perform this parameter update step in the epoch loop, we have these two lines here. So the first one is to fetch the gradient. And so we're just going to call this function compute gradient and feed in the corresponding X and Y and theta values, parameter values. And our gradient function is already set up to do this, computing the sigmoid of the matrix product of our data and the parameters, and returning the gradient expression that we showed earlier, which was based on kind of derivative of the binary cross entropy or the negative log likelihood expression specific to the sigmoid or logistic function. And then the second step was to perform a step. So we have this theta value, and what we want is a new theta value. And we can do this by with the minus equals here, or in R, setting it equal to the current value of theta minus this term here to get an updated value of theta. And so this term here is, of course, going to be the learning rate, the step size, times the gradient, and then times this annealing term here, 1 minus epoch divided by the total number of epochs planned. So that was to perform the update. And then for the actual prediction function here, we simply add this matrix product, the dot product between our data matrix and the parameter vector here, X and theta. And that's going to give us our logit. And what we want then is a probability. So we're transforming the logit into a probability by using the sigmoid function. So we again utilize the sigmoid function that we've created up here. And that's going to give us a probability. And that then is the result that we want to return from this prediction function here. And if the probability is above 0.5, so here we've added a threshold, then we're going to make a call. Is it a 1 or is it 0?